Let's get started. Hi, everyone. Great you're back for the third week of the WOMANIUM Global Quantum Program. I will share some announcements and the program for today, and then we will start a very exciting session with Zurich Instruments today, and after that, advanced quantum testbed with a lab tour. First of all, 2 weeks of the WOMANIUM Global Quantum Program have passed, and you have all been working on Q-bronze, Q-nickel, quantum key distribution, and the first quizzes for hardware and software. Really amazing work, especially that already more than 440 people finished Q-bronze, which is an optional module, and will now get those certificates awarded. This is a record for Q-bronze in one course, 440 people, in addition to 300 people already having Q-bronze or starting with Q-nickel right away. So great work. We are really happy, and these certificates will be issued the next few weeks by QWorld. Then there has been extreme buzz on social media, on the Discord. We have been really happy seeing people share about the achievements in the program, seeing people share about the scholarships being awarded, and then also about the progress on the global quantum projects and other works. Here, for example, by Carolina, who has been teaching girls in Venezuela about quantum in sessions, and now creating flyers for it and spreading the word. Please keep on doing it, and it is wonderful to see the activity on Discord, LinkedIn, and elsewhere, and grow the community and spread the word about quantum. Today, we will kick it off with a hardware bootcamp, interfacing a qubit the easy way. This bootcamp will be held by Zurich Instruments, by ARASH, FEREIDOUNI, and BRUNO, KUENG. We really look forward to it. This will be followed with a collaboration with Advanced Quantum Testbed, where we will show the great facilities of superconducting qubits and more, and discuss more about how this interfacing a qubit is really brought into practice. Tomorrow, we will continue with silicon-based quantum computing and a keynote on quantum scalability, climate, and entrepreneurship, and then even more virtual lab tours. Time to start with the hardware bootcamp by Zurich Instruments. Here with me is ARASH FEREIDOUNI. He is an application scientist in quantum technology at Zurich Instruments and has been a great collaborator of ours the past year. ARASH research is focused on both theoretical and experimental quantum physics. He has a really strong background in experimental quantum devices for 2D magnetic and topological materials, focusing on Weil and Dirac semimetals. That is what he did his PhD in, and after that he joined Zurich Instruments office in Boston, Massachusetts as an application scientist, working with groups all across the United States. And not only ARASH is here from US, but also colleagues located in Zurich. So we look forward to a wonderful global session. Please share more about Zurich Instruments, ARASH, and then take it away with the presentation and videos.
Thank you, Marlo, for your kind introduction. My name is ARASH, and I'm an application scientist with Zurich Instruments, our Boston office in Massachusetts. So today I have the pleasure to welcome everyone to interfacing a qubit the easy way. In the course of next hour and 15 minutes, we will learn about how to interface various qubit modalities, and specifically we will focus on superconducting qubits. To begin with, let me try to go to the next slide. To begin with, Dr. Chuni and she will give us an introduction to Zurich Instruments and our company. She is a product manager in Zurich headquarters. This will be followed by my presentation on various qubit modalities and how to interface them. And then after that, we will focus on superconducting qubit and hands-on characterization of superconducting qubits by Dr. Bruno Kang and Dr. Michele Collado. This happened at ETSC PSI. And this will be the materials for this hands-on qubit characterization is available through the links that you see. My colleague will copy those links in the chat. and you will be able to access those materials, download the manual, or download the Jupyter notebooks. We will talk about those materials again. This will be followed by a lab tour at Advanced Quantum Testbed, and AQT is one of the forefronts of research in superconducting qubits. Then after that, we will have a Q&A session with both Zurich Instruments and AQT scientists. With that, let's watch a 30-second video.
What about your research project? We would be thrilled to hear more about it. Get in touch with us and let's talk.
Let's take an overlook of what are different type of qubit modalities and how to interface those qubit modalities. So Zurich Instruments, as mentioned, is involved into the control and measurement systems for various qubit modalities, such as superconducting qubit. Now, for example, for neutral atoms and neutral qubits, there are essentially Rydberg atoms arranged in the lattice. They're usually alkaline or alkaline atoms, and then you can use the optical tweezers to move around those atoms in the real space. The information is encoded into the hyperfine energy levels. And usually you want to operate those qubits at a temperature as low as hundreds of microkelvin. This is achievable by laser queuing. You can also operate those qubits by microwave or laser. Another qubit modality is color centers. They are usually nitrogen vacancy or silicon dye vacancy centers. And the information is encoded into the spin states of those NV centers. The transition frequency is adjustable by adjusting the magnetic field, and usually you operate them from room temperature down to the very cold temperature if it's an assembled room temperature. Optical and microwaves are used to manipulate those qubits. Another type of qubit modality are spin qubits. Essentially, spin qubits are confining of a charge carrier in a very small region, real space region, and you can confine them in various materials such as silicon, transition metal dichalcogenides, and so on and so forth. Then you can encode the information in energy levels of Zeeman splitted energy levels. The temperature you usually want to operate the spin qubit is few kelvins, less than 4 or 3 Kelvin. And you can use magnetic field, electric field, or microwave to address those qubits. Finally, the last but not the least are superconducting qubits. They can be various architectures such as Transmons, Fluxonium, Gatemons, and so on and so forth. Essentially, superconducting qubits are nonlinear harmonic oscillators. And the nonlinearity comes from the Josephson junction in the circuit. You can operate those qubits at temperatures as low as 10 millikelvin, and that's achievable by dilution refrigerators. And now you can use microwave pulses and so on to control those qubits. So let's get into more details and see how to interface each of those qubits. First, the neutral atoms. As mentioned, the development in the optical tweezers resulted into many developments in neutral atom quantum computing. Essentially, optical tweezer is a potential well that can trap an atom, and you can move that atom in around the real space. The microwave and radio frequency is used to control various components of neutral atom setups. They are very complex setups. They have lasers, many up conversion and down conversion, and they have various type of electronics connected to those systems to control them. One of those electronics and the component that you can control is acousto-optic modulator. The acousto-optic modulator is connected to HDAWG. It stands for High Density Arbitrary Waveform Generator. So you can play pulses and waveforms on the acousto-optic modulator. The requirements usually in these setups is to be able to chirp up the frequency, stay at that frequency and chirp down. And that's usually gonna take milliseconds of staying there. So your arbitrary waveform generator is limited by memory, and the requirement is to be able to play long waveforms. Our solution is with a play hold function that you can send a tone to the acousto-optic modulator and stay at that frequency for as long as you want. Then you also want to be able to control those components in the baseband, few hundreds of megahertz. Let's get a little bit more complicated setup, and that's basically through the NV centers. Here you have a SHF-SG. It stands for Super High Frequency Signal Generator. And with that diagram, the block diagram that you see on the right side, using the SHF-SG, you'll be able to control various acousto-optic modulator that's in front of various lasers, for example, green, yellow, and red. And the green laser is used to control the charge state and yellow state for a spin state. Then you can use the microwave antenna and microwave to address the state of the system, and you can send pulses through the output channel of SHF-SG. Those pulses are already IQ mixed, and essentially each output is an arbitrary waveform generator with built-in up conversion. So with one line, you're able to do your experiments. Now you can add multiple lines to do more complex setup. And then with avalanche photodiode, you'll be able to do the readout through essentially the excitation, the fluorescence lights that go to the avalanche photodiode will go to a counter, so we count the states. A little bit more complex setups are spin qubits. For the spin qubits, you have various confining gates, and you have tunneling gates, and you use both DC sources as well as a higher frequency, such as HDAWG, in addition to lock-in amplifiers and quantum analyzers to be able to interface them. For example, if you look at the HDAWG, you can produce your IQ tones, send it to a mixer, and that mixer output will be used to control the oscillating magnetic field that will be used as a gate to operate the system. You can have 2 qubit gates, and by sending very fast pulses to them and having the tunneling gates operates with the HDAWG. In addition to that, you'll be able to use lock-in amplifier, MFLI, on the right, bottom right side of that. That will do the characterization for you. And on the bottom left side of that is the UHF-QA, that's the quantum analyzer. So on the MFLI, you'll send a tone, pass it through the set of your sensors, and go back to the MFLI, which is a current amplifier, and you can do the characterization. On the UHF-LI, you can send a tone through coupler, and using the RF reflectometry, you can do single-shot readouts. Essentially, RF reflectometry is the detection of the change in the impedance of your sets of sensors as the impedance change when the qubit state changes. And there is a tank circuit connected to that, that sets of sensors. So increasing with this trend of increasing the complexity, we go to the superconducting qubits. Various type of devices are used to interface them, and essentially the superconducting qubits are coupled to their resonators, and also you can have it capacitively coupled, and also they're coupled to the signal generator for the control and measurement. So the measurement happens through the SHF-QA, super high frequency quantum analyzer, and that will send tones and signals to each resonator, so we can measure the state of the qubit through the resonator. You can do the multiplex readout, so one line will be sufficient to measure each resonator separately. up to 16 qubit you can control with one channel. Then you will use the pulse generator and to apply gates to the qubits, and that's using the SHF-SG signal generator. So the pink lines that you see goes to the qubits, they are the lines to apply gate voltages to them. And essentially, you can also use the HDAWG, again, it stands for high density arbitrary waveform generator, to send flux pulses to the qubits. You can use precompensation to compensate for any waveform shape in that flux pulse. And all of these instruments should work in harmony, in the harmonic way. So the PQSC, programmable quantum system controller, is essentially the controller that connects all of these devices together and provides some fast feedback, so you'll be able to send pulses back to back and measure it back to back. So now we know about the higher level of hardware and how it's connected to various qubit modalities. The question is that how to control this hardware, what software do you use? In our company, the solution is clear. We use Lab1Q to control the hardware. Lab1Q, to give you an overview, is essentially a program that can help you to write your higher level quantum circuits. Essentially, you can imagine this circuit that is very simple. You play a pi half pulse, followed up by some delay, and you play another pi half pulse. And then that will do the measurements. You'll do the measurement. So that's how the code will look like on the Lab1Q. You have a section that there are some pulses played in that section, pi half pulse, followed up by some delay and another pi half pulse. And the pulse sheet viewer will show you how does it look like in the time domain. This will be followed by a signal going through the measure line and the signal that comes to the input line through the acquire loop. So this is called pulse sequencing. Essentially, pulse sequencing is very important in interfacing the qubit, because you have a very limited coherence time, and you don't want to interact with the qubit for a very long time, because it can introduce various type of noise, dephasing noise, and so on and so forth. So you want to interface a qubit in a pulse, and the pulse has various characteristics such as pulse shape, frequency, phase, and so on and so forth. In each pulse shape, pulse envelope, you can have various type of modulation, amplitude modulation, frequency modulation, and so on and so forth. Now, the question is that what is important in pulse sequencing? And that's where Andreas will give us some details about the importance of pulse sequencing.
Finding the right pulse shapes is very important for your quantum experiments and getting to highest gate fidelities. Hi, I'm Andreas, and today I will show you how Lab1Q can support you in defining your pulses and pulse shapes, and then also refining them. Before we start, we import everything that's important for Lab1Q and define a simple device setup where we use emulation mode, which actually allows us to run everything without being connected to quantum hardware. And that also means that you could run the notebook straight away on your computer at home. We use a simple calibration and connect to our emulated session to be ready for the experiments. First, of course, we want to define a pulse. And here we use a track pulse out of our pulse library with a length of 400 nanoseconds, an amplitude of 1, and a track parameter beta of 0.3. That's our X90 pulse. To find the right energy of our X90 pulse, we want to sweep its amplitude first. So we define an amplitude sweep, starting at 0.1, ending at amplitude of 1 with a count of 5. Now we can put both pulse and amplitude sweep into our experiment, where we first use an acquisition loop in real time, and then a sweep loop that tells Lab1Q that we want to sweep amplitude, the amplitude sweep parameter. In the play command, we want to play the X90 pulse defined above on a signal line called drive, with an amplitude defined by the amplitude sweep. After defining which line actually is what we call drive. We map it, we run the experiment, and we can have a look at the simulated output of the instruments. And we see indeed a parameter sweep of 5 steps where the amplitude of our drag increases from 0.1 to 1. Blue is the real part, red is the imaginary part of the pulse. Sometimes, however, you want to have sample-precise control over your pulses. Say you want to define a NumPy array and then play exactly that array. And you can do that, of course, as well by defining sampled pulses. It can be done as is shown here. We define 2 pulses for illustration, one that is purely real and has 1024 samples, and the other that is complex and has 128 samples. We sample actually random numbers, because I don't have better data at hand now, and define the pulse. First the real one with the real complex with the real numbers, and then the complex one with I and Q data. Now these pulses are ready for use. You have noticed they don't have any parameters such as the drag parameter, but we can still sweep amplitude or phase of the pulses. And we do that in this experiment. We define an amplitude sweep that goes from 0.1 to 1 and a phase sweep that goes from 0 to pi over 2, both in 5 steps. We include the sweeps in our experiment, run the experiment and look at the output. And it is, as expected again, for the longer pulse, which was the real pulse, we see that the phase slowly transitions from 0, purely real, to imaginary 90 degrees in step number 5. And for the complex pulse, we see that the amplitude is increased linearly here.
Dr. Shunyan Shi has the sharing capabilities right now. So before continuing with the presentation, I'll let her to take over and then we'll continue after that. Thank you, Shunyan.
I'm Chunyan, application scientist and also product manager from Zurich Instruments. And it's a really great pleasure to give a company overview in WOMANIUM Quantum 2023. Zurich Instruments is founded in 2008. It is spin-off from ETH. With the leading technology, the company grows really fast. So far, we have more than 170 people and really from more than 20 different nations. The headquarters is in Zurich, and we also have local representatives and worldwide partners, and which really allows us to support our local customers with a timely and effective way. In 2021, Zurich Instruments becomes Roden Schwarz, a family member. This is to strengthen Roden Schwarz proposition in scientific realm and with the common goal to accelerate quantum technology and quantum computing development. Our quantum mission is to help scientists and researchers build practical quantum computers. So we develop electronic control system that is specialized in superconducting qubits, semiconductor qubits, solid-state spin defects qubits, and many other types. And development work started since 2014, and so far we have 9 years experience in quantum computing control system. And here you see is our quantum computing control system roadmap. We are focused on not only scaling thrust, but also technology thrust. At current stage, we can support quantum qubit chip with more than 100 qubits. And we have developed quantum specific products. Here you see generation 1, which is based on IQ mixing. This is a baseband products. And generation 2 based on double superheterodyne technique and directly go to a microwave frequency range. More than that, we also developed the quantum computing control software that Lab1Q, you already see part of that, and you're going to hear more in the later sessions. Driven by the quantum mission, we are actively contributing to the research projects since the beginning. And this projects not only in Europe, but also in other countries and regions. And here lists all the ongoing projects and also partnership. We really grateful with our wide customer base, which are not only from academia, for example, ETH and Berkeley, but also in industrial. For example, the commercial quantum computer company, IQM, and Intel. And we're so proud of the achievements, milestones from our customers. And we see gradually the breaking news in all the nice publications. And this is really strongly motivate us to work harder and also to more close to our customers to really speed up the development of quantum computing. This is a short company overview. And write us if you have any comments or questions. And of course, if you're interested in Korea, we also have a lot of open positions on our website. And we are very much looking forward to talk to you.
Great. Thank you very much, Chunyang. There are already questions about the technical part for ARASH and you, and namely the question.
We were on pulse sequencing and pulse shaping, and Andreas told us how to do pulse shaping with Lab 1Q. Now, the next step that you have pulses, you want to combine those pulses into a section. Essentially, when you run a quantum experiments, it's combined of various sections. You want to combine all of those sections together. For example, in the simple experiments that I showed you earlier, when you play a pulse followed up by some delay and another pulse, then you have one section, we can call it the excitation section, and then this will be followed by a measurement section. Now there is a parameter, the delay that you want sometime to change, for example, for a Ramsey interferometry, and then this will happen through looping around various sections back to back and sweeping over time in that Ramsey interferometry. That gives us the next level of access to the higher level of an algorithm, a quantum algorithm that you can see, for example, the surface 17 qubits algorithm, and then you can focus on the Z stabilizer side of that. So the code will look like something like this, very small, very concise in the Lab 1Q. And if in each section you click on that section, you will be able to pulses play it in that section. And if you click on the pulse, you'll be able to see the I and Q components of that pulse. And again, that comes back to the question that Marlo asked about the complex pulses that are playing on the devices. So having that, let me also remind you to how to get the materials required for this hands-on experience. One way is through our website. So go to the support, zinst.com, ZHINST.com, go to the support, download the manual, the Lab 1Q manual, and you'll be able to run on the Lab 1Q. But also for the experiments and some examples, go to the GitHub. On the Zurich Instruments GitHub, click on the Lab 1Q examples, and then go to the Qubit characterization. And that will be followed by many Jupyter notebooks. And those Jupyter notebooks, the first line usually has the emulates mode. If you don't have the Zurich Instrument devices, you still can use Lab 1Q through the emulation mode and run all of these experiments without having a qubit and a device in your hand. Just put the emulate on true, and we'll continue with that one. With that, I'll share Dr. Bruno's presentation on how to interface superconducting qubit characterization, and I'll be back with you after that.
I'd like to begin this part a bit broadly with the question, why are we interested in superconducting qubits? What is great about them? And the superconducting qubits actually combine a number of nice properties. They show really good coherence properties, and it's possible to control them fully electrically. No need for lasers, for instance. You can fabricate them using microfabrication technique, which is an advantage when scaling up system sizes. And it's been shown that you can combine this also in hybrid technologies, for instance, combining them with semiconductor or Rydberg atoms or NV centers. And with this many advantages, they actually have found applications in all quantum technologies. The largest one probably quantum computing, but just as well quantum simulation, quantum communication, and quantum sensing are fields where superconducting qubits are used. And the most frequently used type of qubits is the Transmon qubits, and this is also the type that we'll look at in this webinar in more detail and that we use for the measurement. So let's start at looking at what is the Transmon qubit. Essentially, it is almost an LC oscillator that is fabricated typically using aluminum on silicon substrate. Here on the right-hand side, you see an image of a device from Quantum Device Lab at ETH. And it's almost an LC oscillator, but not quite. So the inductor in the LC oscillator is replaced by a Josephson junction, which behaves as a very nonlinear inductor. And while a linear LC oscillator would have a quantum state ladder, which is equidistantly spaced, here already the transition from the second to third excited state, or first to second excited state, is strongly detuned from the transition from ground to excited state. So by controlling this system with a single drive tone resonant with the lower transition, you can only access these first lower two levels, and this is a qubit that you can use in quantum computing or other applications. Now going one level out, so this is a single qubit, but we also need to interface it. We need to bring signals in and out. We need to measure qubit state without perturbing its state, and we may want to couple multiple qubits. And these challenges are actually met with solutions based on coplanar waveguide engineering. Here you see a photo of a bit a larger scale of the same sample, where you can recognize control lines that actually can go right to the qubit to provide electrical and magnetic bias. And in the circuit QED architecture, which is often used with transmons, the readout is realized by passing the signal from the actual signal line through a resonator to the qubit, which can be thought of like a filter, so still isolating the qubit state. And then coupling circuits can also be realized as simple transmission lines, coplanar waveguides, as seen here, or you can place more complex circuits in between to tune the coupling as well. And in terms of connectivity here for the experiments that we look at today, we need only 3 of these lines, so a pair of input-output lines. See, these are the blue lines, the readout line, and then a single control line, which is the magenta line. One step up, the macro view. These experiments happen in a dilution refrigerator, and this is a photo from an actual setup at ETH PSI quantum computing hub. And the dilution refrigerator that you see in the background provides nowadays a large sample volume down at 10 or tens of millikelvin temperatures, and the sample which resides down there is connected to with many lines. Actually, in quantum computing, it's especially a large number of lines, so you have high density wiring with including cryogenic microwave components such as amplifiers. And then at room temperature, you have a setup of instrumentation. Often it's a full rack or that scale with instruments with high requirements in terms of signal quality combined with high speed. And then these are high-end instruments that are needed for that purpose. Symbolically, in the end, all we do is send signals in and out, which is true, and we'll look at it in more detail in the following. So concretely, what do I need to measure a single qubit? And from our company, there's a clear answer in terms of what you need in terms of hardware and software. And in the hardware side, it's the SHF QC, qubit controller, which is an instrument combining all the microwave control and readout signals that you need in one box. You can get it as a 2-channel versions with 2 control channels and 1 readout channel, which is upgradable in the field, so fits small systems and provides a scaling roadmap too. And it operates from DC to 8.5 gigahertz without mixer calibration, so you can often connect the signals right from the connectors to the cryostat, that there's no need for extra amplification or other components. And on the software side, with LabOneQ, we can provide a fully Python-based measurement framework enriched with graphical tools, for instance, for pulse sequence viewing. And this software allows you to design your experiments on a high level rather than programming instruments or hardware in that sense. And it comes with a ready selection of examples that are tailored or application specific. For instance, all the measurements that we show today are contained in these example libraries. So to wrap this up, so how are these signals connected to the instruments? We have the pair of input-output lines from the what we call the quantum analyzer on the left part of the instrument, and then 1 line from the signal generator connected to the Qubit charge line. So moving to the towards measurements, the first thing is we need a signal. So it's good to look at quickly how this signal comes about, how we get a measurement signal from the qubit. In the circuit QED architecture that I mentioned, this is achieved by measuring a resonator, a signal passing through a resonator. Namely, if you measure actually a resonator transmission function, you would get maybe such a Lorentzian transmission curve in amplitude, as you see the solid line here marked with G for ground state. And because there's a coupling between the resonator and the qubit on the chip, the resonator frequency will change when the qubit state changes. And we can exploit that by measuring at a single frequency here, fMES, and looking at the amplitude and phase at this frequency will give us a contrast between ground and excited state. How to get to this point, to this configuration, we need to do 2 steps in spectroscopy. The first is the resonator spectroscopy, where we just characterize the basic properties of this readout resonator, frequency and the line width, and get things ready to have a basic qubit readout signal. And then qubit spectroscopy, we find the qubit frequency, which is the most important parameter, but then there are also anharmonicity or an upper bound for the T2, which we can obtain from the qubit spectroscopy. Looking first at the resonator spectroscopy, what is it? It is a microwave transmission measurement, and the SHF-QC, in the SHF-QC, this is done by the quantum analyzer part, which generates and analyzes the necessary signal in the digital domain, and then also up-converts and down-converts that in an analog stage using a shared local oscillator between generation and analysis. This allows us to do a phase-sensitive measurement and get the best phase stability for this measurement as well. The signal amplitude in the sample is really low actually, so it's a level of a few photons in the resonator that we aim at, and to get to these low signal levels while still having a good signal to noise, what we do is we attenuate the signal from room temperature down to the cryostat to suppress the noise at room temperature, which is thermal noise plus instrument noise, to suppress it below the thermal noise level at base temperature. And then on the way up, we have typically high Hemd amplifiers and cryogenic Hemd amplifiers, as well as sometimes a parametric amplification stage. And this latter one, the parametric amplification, would give us a readout which is quantum limited, so the only remaining noise source is the quantum noise, and all technical noise sources are suppressed. So this was the resonator spectroscopy. So then, having obtained this line shape of the resonator, we move to qubit spectroscopy, and we have to ask the question, what is the correct readout frequency? And in asking this question, we remind ourselves that this is a complex measurement signal that we look at, and so the complex amplitude A, and the quantity that we want to maximize for is the difference in complex amplitude between the signal in ground and in excited state. Starting from resonator spectroscopy alone, we cannot fully determine what is the optimum frequency, because in that picture you see here we only have the solid trace but not yet the dashed trace. So we can make a first simple guess and pick the center frequency of the resonator, which will give us sufficient amplitude contrast for the next measurements, but keeping in mind that fully optimal choice of this measurement frequency would require us to measure this contrast between the signal difference as a function of fmesh. And for this measurement in turn, we need a way to excite the qubit into excited state as well, so to get both the solid and the dashed curve, if you will. Qubit spectroscopy is, for qubit spectroscopy, we add one more tone. We perform a two-tone spectroscopy measurement where we fix the frequency that we use for the qubit readout. So this is the left part of the circuit. And then we add a signal from the signal generator, of which we sweep the frequency. We can do this measurement both as pulsed or as a continuous wave measurement. In the continuous wave measurement, we just have both tones on, whereas in pulsed, we apply control, qubit drive pulse, then a readout pulse, and then we repeat this measurement many times. And both approaches have their advantages. So in continuous mode, you would get the highest duty cycle, but in turn you have to worry more about the interaction of the qubit drive and readout, and pay more attention to the powers that you apply. And on the keyword of the powers, so we have not talked about the readout powers too much, but rather about the frequencies. But powers are important parameters as well. And namely, when we look at what happens at higher drive power, for instance, this is the left side of the slide, what we would get is generally a saturation of the qubit population, which leads to a saturation of the qubit spectroscopy peak height, but also a broadening of the width. And if we go to the low power limit, where we narrow the peak and then also observe a reduction of its amplitude, we can go to the regime where we see the intrinsic line shape of the qubit and get an upper bound on T2, or lower bound maybe. Then in turn, going to higher powers, we will see additional peaks typically, for instance, GF half transition, which is a signature of a two-photon process, bringing the qubit from ground state to the second level, excited state level, the F level, and this may be used deliberately to measure actually the anharmonicity of the qubit by measuring this peak's position. Then this was control. Then there's a readout power as well. So here the effect to be aware of is the AC Stark effect, and the AC Stark effect would cause a shift of the qubit resonance peak as a function of the number of photons that are in the readout resonator, and the average number would determine the shift that we see, and this photon number also fluctuates, which leads to a broadened peak as well, and leads to dephasing, and normally both these effects we don't want to have in the end, so we also need to measure at low readout powers to avoid these effects of measurement back action. Yeah, and with that, I'd like to conclude the theoretical part and then hand over to Marek and Michele, who will guide us through these spectroscopy measurements on an actual setup.
Thanks, Bruno, and greetings from the lab. We are here at the Paul Scherrer Institute, or in short PSI, where today we'll have the opportunity to demonstrate qubit tune-up on a real sample. I'm here with Marek Pechal, researcher in the Quantum Device Lab at ETH Zurich, who's responsible for the setup of this lab. Marek, can you tell us a bit about your group and its research mission?
Hello, Michela. Absolutely. It's a pleasure to welcome you and our viewers in our lab here at PSI. So we are part of the ETH Zurich PSI Quantum Computing Hub, which is a joint center established just last year in order to develop quantum computers, specifically quantum computers based on superconducting circuits and trapped ions. Our group in particular focuses on the superconducting circuits architecture and on the potential challenges that one might encounter when trying to scale up quantum processors. And as part of PSI, we're also aiming for close collaborations with industrial partners such as Zurich Instruments, which we hope will help develop scientific instruments for use in quantum computing.
Sounds exciting, and it's great to be a part of it. So now, as we see, there's already experiments going on, and we are curious to learn more about it. Can you explain to us what's going on behind us?
Yes, so what we can see behind us is an example of a large-scale superconducting quantum computing setup. The central parts of this setup are the dilution cryostat, which houses and cools the quantum device to millikelvin temperatures, and this rack of measurement and control instruments in front of it. In fact, many of the instruments that we can see here were developed in collaborations between academia and industry. This whole setup then operates a 17-qubit device, which we use to realize an error-corrected logical qubit based on the surface code architecture. And that's a very important skill to master, because error correction is crucial if we want to operate a large-scale quantum computer in a fault-tolerant way, even in the presence of energy losses or noise. And running these fault-tolerant experiments requires extensive calibration and tune-up of the whole device. And in our demonstration today, we would like to look at some fundamental measurements for single qubit tune-up. And to this end, we have picked one of the qubits, and we have made the necessary connections to control it with a single SHF-QC instrument. For this, we just need 3 connections. So the output of the signal generator is connected to the qubit's drive line, while the input and output of the quantum analyzer are connected to the readout resonator feed line.
Thank you for your explanations. And now that we know a bit more about the setup and the lab, let's get started with the experiments. Let's dive into the measurements. The first step in qubit tune-up is the resonator spectroscopy. Here, the goal is to find the readout resonator center frequency and characterize its line shape, so we know what readout frequency to use for the subsequent qubit spectroscopy. It is a microwave transmission measurement in which we apply a continuous readout tone, sweep its frequency, and demodulate the return signal to obtain transmission amplitude and phase. So, let's carry this out and look at the data. We see here a characteristic line shape at 6.92 GHz with a width of a few megahertz. We can perform a fit and obtain the frequency of the minimum. This frequency is often a good starting point to use as readout frequency for the qubit spectroscopy, but let's note that it's not necessarily the optimal one. In qubit spectroscopy, we will now keep the readout frequency fixed and turn on the qubit drive. Here, we sweep the frequency of the qubit drive and expect to see a peak or dip in the signal when we hit the qubit resonance frequency. Knowing this frequency allows us to then conduct pulse characterization measurements, such as Rabi oscillations or lifetime measurements. In view of these subsequent steps, we have set up the qubit spectroscopy as a pulsed measurement, rather than as a continuous wave measurement. At each frequency point, we play a number of qubit drive and measurement pulses after one another. Let's look at the result. We have here already tuned the drive and readout powers low enough to clearly identify a peak in the spectroscopy signal. Its position and width tell us the bare qubit frequency and give us an indication of the qubit lifetime. Normally, we would start by finding the approximate qubit frequency at higher drive powers. With a strong qubit driving, we would also see other effects. For example, a shift of the peak position and a change of its shape, or the appearance of other peaks, notably the GF half transition. Let's look into the software mechanisms behind this measurement. I'd like to highlight 4 elements of the Lab1Q software that we use in practice. These are the device setup object, the calibration object, the qubit database, and the experiment object. The device setup object allows us to specify the structure of the hardware setup. Which devices do we use, and which signals of these devices? In this case, we have one device, the SHF-QC. We use 2 output signals for resonator and qubit drive, and 1 input signal. We can name these signals in a logical way according to where they are connected. The calibration object allows to handle the hardware settings, such as oscillator frequencies or drive amplitudes. It allows us to access and modify some of these parameters for the purpose of a specific experiment. One example shown here is, we set a hardware oscillator frequency to an appropriate value we know from the qubit parameters. And that points us to the next element, the qubit parameters. We want to keep track of the qubit parameters separately from the hardware settings, and therefore we store them separately in software. We store the qubit parameters in a Python dictionary, which contains things like a T1 time or a drive pulse length for each qubit. We would maintain and update this database throughout the tune-up and always take this updated database to re-specify a new setup calibration. Finally, the experiment object represents one specific measurement, such as a qubit or resonator spectroscopy, described on a high level. To turn this experiment description into an actual measurement, the software does 2 steps. First, it compiles the high-level experiment into a hardware program, and second, it executes the program on the hardware and returns the data. Based on these data, we can do an analysis, such as a fit, and then feed back the analysis result into our quantum device database. At this point, we obtain the qubit drive frequency, and we update the corresponding parameter of the qubit database.
Now in the second part, we want to go from spectroscopy measurements to pulsed qubit control. And for these measurements, it's useful to remind ourselves of the representation of a qubit state on the Bloch sphere. Namely, I can represent any state, psi equals alpha g plus beta e, where g and e are ground and excited state, as a point on that sphere. And the north and south pole correspond to the states g and e respectively. And the longitude and latitude angles of the point correspond to the relative phase between alpha and beta, or map to the relative amplitude between these two. And how does this relate to control pulses? So if we take, for instance, a resonant drive pulse that we apply a pi half pulse, this would bring us to a point on the equator of the sphere, and the angle at which we rotate the state on the sphere is proportional to the integral under the envelope of the pulse. So if we double that by scaling the amplitude, we would get to a pi pulse that brings us to the excited state at the south pole. And the role of the phase corresponds to mapping the state on the equator of the sphere, for instance, taking this pi half pulse, but applying a 90-degree shifted pulse would get us to a 90-degree shifted position on the equator. And generally, due to the really proportionality of the final state with the phase and amplitudes of the signals, it's also apparent that these analog properties of the signal need to be really well controlled, stable, and noise-free to allow us to accurately control a qubit state. Now, how to get to this point where we have dedicated pulses to move us around the Bloch sphere? The first step to that is our Rabi oscillations. And the basic principle of these measurements is that we apply a certain control pulse, and immediately afterwards read out the qubit state. So this would rotate us some angle on the Bloch sphere, and then we vary the amplitude of that pulse systematically, which would guide us through a rotation on the Bloch sphere. And the readout after this control pulse gives us a projection of the qubit state, a signal proportional to the projection of the qubit state onto the z-axis, and the implementation of this measurement is done using a pulse sequence that you see here at the bottom of the screen. So you would apply a burst of control pulses with varying amplitude, always followed by a readout pulse right after. And since we need to obtain quantum statistics to get a final sensible measurement data, we repeat this measurement many times. Some practicalities of this measurement. So first, about the drive and readout pulses. So the drive pulse, generally we want to apply a short pulse. That's advantageous as it allows us finally to apply a fast gate rotation. The disadvantage of shorter pulses is that you increase generally the leakage to higher excited states. This you suppress from the start to some degree by choosing a Gaussian envelope, which has really well-decaying spectrum at its tails. And further optimization is possible, for instance, by doing a drag pulse calibration where you tailor the spectrum to suppress, for instance, the transition to the F level and zero that out. For the readout pulse, generally also, you want to have a fast readout. As you reduce the readout pulse width, you of course get less signal, and generally you want to exploit to the best possible the measurement in this available time. A square pulse is what gives you the best integral for a given max power, and for further optimization, what you can do is pre-emphasis of the pulse to speed up the ring up and ring down times of the readout resonator. In terms of timing and averaging, it's important that the control and readout pulses are well aligned, ideally with no significant gap between them. So synchronization is important, and also taking care of the signal processing propagation delays to avoid an overlap of the pulses at the sample. You need to respect a certain relaxation time after each control readout pulse pair, and going for 3 to 4 times T1 would get you to the percentage level of residual excited state population. To speed that up further, you would need to implement active reset, which is actually rather straightforward with the SHF-QC. Then in terms of averaging, even if there's no technical noise, you still need to do quantum average over quantum statistics, and maybe 10,000 averaging here will also get you to the percent level of residual errors. Finally, then what you get are data that can look, as you see here on the right, sinusoidal oscillation of the averaged amplitude or readout signal that you have. And you can fit the sinusoid to it to obtain pi and pi half pulses. And we'll see later how this looks in practice. Beyond the Rabi oscillation measurements, you can do a suite of the 3 types that are often done together, Rabi, Ramsey, and T1. And going from a Rabi oscillation to a Ramsey, you take this calibrated pi pulse from the Rabi oscillation, and in the Ramsey you apply 2 of the pi half pulses and vary the separation, the waiting time between them, to obtain Ramsey fringes, which are a signature of the free oscillation of the qubit, and the frequency of these oscillations tells you the difference frequency between your drive and the actual qubit frequency. So this is a means of measuring the qubit frequency really precisely. And the decay of the oscillation gives you the inhomogeneous dephasing time. T1, lifetime measurements. Here you start with a pi pulse obtained from the Rabi data, and you vary the separation between a pi pulse and a readout pulse, and this gives you a decay from the excited state back to the ground state, so the T1 time, or the decay time that you measured there, is the qubit lifetime T1. And now again, back to the lab, back to Michele, who will show us the Rabi oscillation measurements in practice.
Now that we have determined the qubit readout and drive frequencies, we can move on with the Rabi oscillation experiment, which is the first step in characterizing the coherence properties of the qubit. The core element of this experiment is the application of a drive pulse to manipulate the qubit state, followed by a readout pulse to measure the state. The drive pulse rotates the qubit state on the Bloch sphere by an angle proportional to the pulse amplitude. By repeating this measurement for varying pulse amplitude, we can track this rotation on the Bloch sphere, starting out at the ground state, through the excited state, and back to the ground state. That's the Rabi oscillation. Let's start this measurement. It takes about 2 minutes, and while it is running, let's look at the software implementation. This experiment is great to illustrate the experiment definition based on the Lab1Q section concept. The Lab1Q sections allow us to define the temporal schedule of an experiment on all timing levels, starting from pulse shapes, over timing alignment of pulses on multiple signals, up to sweeping and averaging loops. For the Rabi oscillation experiment, we see here the section layout written in the Lab1Q domain-specific language. Let me go through this layout from the inside to the outside. Sections can be thought of visually as blocks spanning over multiple lines of the experimental music sheet. And each of these blocks contains pulses, spacers, or further nested sections. They're stacked from the left to the right, or in the other direction, according to the need. Here, we have 3 blocks in the innermost part: qubit excitation, qubit readout, and delay. Inside the first section, qubit excitation, we place a Gaussian pulse on the drive line by using a play instruction. In the next section, qubit readout, we similarly play a pulse, this time on the measure line. Simultaneously with the readout pulse on the signal output, we schedule an acquisition on the signal input. This is handled in a very similar fashion as a play instruction, using the instruction acquire. Instead of a pulse shape, we specify an integration weight function with which the return signal is demodulated. The first 2 sections, qubit excitation and qubit readout, have pulses on separate signal lines, but we want to ensure they happen after one another. The sections are stacked like in a Tetris game, and to prevent them from sliding next to one another, we can use a reserve instruction, blocking one of the lines, even if there's no pulse plate. Finally, we have a delay section, which contains a precisely specified waiting time which is needed physically to allow the qubit to relax back to the ground state. These 2 sections together describe the pulse pattern that we want to play. Around that pattern, we need loops for sweeping and averaging. On the first level up, we have defined a sweep of the pulse amplitude, and we make use of the sweep parameter down here in the playback instruction. A sweep like this is described in the same fashion as a frequency sweep in spectroscopy. The Lab1Q compiler will then implement the sweep in the appropriate way on the hardware, for instance as a software oscillator sweep, a hardware parameter sweep, or as a series of waveforms. And around all of this, we want to do averaging. Even if our signal was noise-free, we still need averaging over the quantum statistics for this type of experiment. So we wrap a loop around everything where we define the averaging number and also an averaging mode, whether we want to do cyclic averaging or sequential averaging. The full section layout now goes into the experiment object, which, as we've seen before, we can then pass to Lab1Q and let it compile and execute the experiment. Speaking of this, our data are ready. Let's have a look at them. We see a sinusoid oscillating between two quadrature signal levels. At the origin, we apply no drive pulse at all, and the signal is at the level of the ground state readout signal. As we increase the pulse amplitude, the qubit ends up in a superposition between ground and excited state. At the maximum, the qubit is fully in the excited state, and as we further increase the amplitude, we bring it back to the ground state. This sort of data allows us to make a first approximation to the single qubit gate pulses for a pi half and a pi rotation. We use a fit to a sinusoid to precisely identify the corresponding pulse amplitudes at 1/4 or 1/2 rotation, respectively. These pulse amplitudes can then be used in the next steps: lifetime measurements, Ramsey fringe, or single-shot readout optimization.
Now in this last part, we want to understand what advanced readout methods we can apply beyond the type that we have seen in the Rabi oscillation measurements. Namely, these are single-shot readout, multi-state readout, and also multi-qubit readout. And to dive into this, we'll have first a closer look at the signal processing inside an SHF instrument. How does this instrument get from an input signal, a microwave pulse, to an actual qubit readout signal? And it will do two signal processing parts. The first is in the analog domain, where the instrument performs a double superheterodyne frequency conversion, getting the signal from the microwave domain to the baseband, where it's digitized and exists as a complex baseband signal. And then there is a digital signal processing, where this signal is further processed by a weighted integration step and further steps. And it's this weighted integration step which is really at the heart of the signal processing, and this step is represented by the integral formula that you see here on the top. It's an integral over a time-dependent input signal v of t, a complex signal, and the integration weight Wn of t, the complex conjugate of it, where this index n denotes one of multiple integration weight units. And after this integral, we obtain a complex voltage Vn here, which is a single value, and this is further used for the subsequent steps. And if you compare the data acquired as we will acquire it in the following with what we know from Rabi oscillation measurements. So in Rabi oscillation measurements, we also had underlying a large set of these voltage values, Vn or V1, because we only used one integration weight unit. But we looked only at average of these voltages and also only at one quadrature of these averages. But we can also look at the underlying individual data points, and a useful way to plot and analyze this is using histogram or point cloud in the IQ plane, which is represented symbolically here on the right. And this image corresponds to a qubit in a single state. It gets a bit more interesting if the qubit is originating in a superposition between ground and excited, or if it's halfway in ground, halfway in excited state. And then we will expect data which more correspond to this pair of blobs that we see on the right-hand side, where we can read off this delta V GE, the difference in the readout signal between these two states, and also we can compare this with the spread or sigma of the individual blob and get so a first idea of the optimal readout direction, which maps to an integration weight phase, and obtain first idea of the signal to noise ratio. And as we enter the regime where this delta V GE is significantly larger than sigma, we can speak of single-shot readout. One way to get these data and to realize in particular the top right situation, where qubit is half in ground, half in excited, is this pulse sequence on the bottom, where we apply pi pulse or zero pulse in an interleaved way and always read the qubit right afterwards, and this gives us a large ensemble of data points. One really nice thing where this becomes really visible how useful this is to look at data in this way is when there are more excited states present in the data. So for instance, if there's an excitation to the F level present in the data, that's difficult to tell from average data, but in these ensemble data, it becomes apparent as we'll have more than just the two blobs in the data, and we can identify this state. And this may be something intentional in bosonic qubits, for instance, or it may be something that we want to avoid, such as F state leakage. But if we want to go and actually basically engineer our system to use these multiple states, for instance, implementing a drag pulse calibration or implementing F-level reset to deal with the state leakage, we need a means to clearly read out and measure these individual states. And the way to do it is actually to make use of the resources on the instruments, where we have multiple integration weights and dedicate one of these weights for each of the transitions that we care about. And the question that comes there is, what is the integration weight that we need to program for measuring a given transition? The answer is actually rather straightforward. So this integration weight needs to be proportional to the complex conjugate of the difference of the raw signal traces, Vg of t and Ve of t, if it's the transition between ground and excited. And these raw traces we can obtain by a scope-like measurement using the built-in scope of the QA, and obtain a clean such trace with well suppressed noise by averaging. We can program then this experimental trace to the integration weight memory of the different units. And in that configuration here with 3 states, we could, for instance, take these 3 first units, and going from the original data from one unit that's shown on the right, we would get data where we always optimally map one transition onto the in-phase quadrature of the signal that we get, and really get the maximum information that we can have regarding this one transition. We can actually extend this on board to implement real-time state discrimination, because we can apply threshold voltages to a given value to make the decision whether this signal from an integration weight is above or below this threshold voltage. And this gives us then a digital signal of a binary qubit state that we can use for qubit reader for real-time feedback, for instance. And as a last point, so this was a multi-state readout of a single qubit, but we can extend this also to multiple qubits using the same infrastructure of multiple integration weights applied to the same input signal. And just without going too much into detail, we would separate different readout signals from different qubits by separating them in frequency, both on the drive side and on the readout side. And here, for instance, start by having the first 3 integration weight units dedicated to qubit 1, and its 3 states that we use, and then the second triplet for the second frequency corresponding to a second readout resonator and a second qubit. And again, so this was the theory part, and I'm happy to hand back to Michele, who will show us these single-shot measurements in practice.
In this last measurement, we'll show how to obtain single-shot readout data and how to specify integration weights in the quantum analyzer channel of the SHF-QC. Single-shot readout data allow us to further characterize and optimize the readout, and to configure the instrument to perform real-time readout. We obtain this data using a long series of drive and readout pulses. For the drive pulse, we use either the pi pulse that we calibrated using the Rabi experiment, or we use a zero-valued pulse. This gives us two sets of integrated readout signal values, one with the qubit nominally in the excited state, and one with the qubit nominally in the ground state. In order to minimize the sensitivity to drifts, we interleave both acquisitions, those with pi pulse and those with zero-valued pulses. This is the section layout for this experiment. A key difference compared to the Rabi experiment is that we request the data without averaging. We can specify this using the averaging mode single shot. Specifying data handles, Q0 ground and Q0 excited, directly in the acquire instructions helps us in separating the data obtained from the instrument. A useful tool for verifying a section layout is the pulse sheet viewer. We've prepared the viewer in this tab, showing a version of our experiment with shortened delays for illustration. We see on the top half the three experimental signals: drive, measure, and acquire. The sections are visualized as colored blocks, and we can see the interleaved structure, for example, through the colors of the drive sections. Let's go back to the notebook and run the experiment. We then generate a scatter plot of the acquired single-shot data in the IQ plane. We see a clear separation between the data points acquired with or without applying pi pulses. This would now allow us to assign a qubit state based on the acquired quadrature values. An experiment like this provides a good illustration for how we handle pulses in Lab1Q. Pulses are crucial both for qubit control, for instance when we want to optimize a pulse shape for maximizing gate fidelity, and for qubit readout, to optimize readout fidelity. Pulses in Lab1Q are objects that we can pass to play or acquire instructions, and that we can reuse throughout a measurement. We have two basic ways to define pulse shapes. First, by using the built-in PICE library for standard shapes with a small set of parameters, such as pulse length or amplitude. Second, by specifying them sample by sample as a NumPy array, which allows us to apply arbitrary shapes. The nice thing is, we don't have to worry about where to place them in an AWG sequence or where on the device memory we'll have to store them. This is all taken care of by the Lab1Q compiler, and we can concentrate on the physics of the experiment.
To this point, we learned how to control only one transmon. But in this niche area, in the noisy intermediate quantum systems, there's gonna be a need for multiple qubits to compensate for the noise. And that means there are going to be needs for control electronics to reduce in the size and the complexity. That will happen through the increasing of the channel density and having system level access to the devices. Also, you need only one software to control all of those electronics together. In addition to that, you need to increase the performance, speeding up the time required for qubit calibration, and also you need to provide low-level support for these routine tasks. In addition, you want to include the quantum error correction codes. This will happen through many complex research going all around the world. One of them is advanced quantum testbed. So we'll be able to get a lab tour from advanced quantum testbed and see on the forefront of these activities what they are doing, and we will helping them and collaborating them the same way that they're helping us to push the edge of this technology. By that, I would like to conclude, and before the lab tour, we'll be able to do some Q&A session and answer some questions. Thank you.
Great. Thank you very much, Arash. This was wonderful to see how it actually goes in the lab, how it actually goes with the pulses, that where everyone is so familiar with programming and the theory. I see you are arranging some things in the background. Zurich team, could you briefly show again what is contained in the notebooks and what can we now do by ourselves?
Awesome, I appreciate that. Sure. Perfect. So again, I will share the screen on the notebook. Can you go back to the session? Just nothing, I'll take care of it.
We have already received the GitHub link, and then there is a manual there. And now, what are the most interesting notebooks to look at? What can we learn there ourselves?
Absolutely. I'm trying to share that presentation again. So I switched to my own Zoom accounts. That's going to be easier for us. And the parts that you can share here, we're going to share it back in the chat session. So there are a manual on our Zinst website. And the website, if you go to the support and manuals, you can go to the Lab 1Q. So Lab 1Q can help you to start with the emulation mode. And also you should be able to go to our GitHub accounts. The GitHub accounts will give you access to various examples that you can see in this presentation. And hopefully from there, you should be able to get some codes that you need to start with. And Mike, my colleague, will copy and paste the links again in the chat, and we can go from there.
And imagine someone has little time, Arash. What is the one notebook to look at?
Yeah, absolutely. So the one notebook is the Qubit tune-up characterization. So in that examples, there's a notebook Qubit tune-up characterization. It has various sections. And then in that sections, first you're gonna define the emulation mode, and that emulation mode give you access to run through the whole notebook without having a device. Essentially what it does, it provides you with some random numbers, generated numbers, data points that will feed the experiments that you are doing. And in that notebooks, there are 4 or 5 different experiments. One of them starting with a resonator spectroscopy, and that's the part that Bruno showed us. And the other one is after the resonator spectroscopy, you go to the Qubit spectroscopy. It can be both pulse and continuous wave. And then after that, we will be able to do Ramsey, Rabi amplitude, and various type of T1 measurements, T2 measurements.
Now there is a question by Harsha from the US. He seems to be quite deep in the field already and asks, what are the sampling rates and resolution of the DAX 16-bit?
Awesome. Maybe Bruno, you want to answer that one?
Yeah, so hi everybody, first of all. Thanks for that question. So the SHF-QC, which we used for this measurement, it has 2 gigasamples sampling rate, both on the outside, on the output and on the input. So this is symmetric, and it's 2 gigasamples complex sampling rate. So this gives access to actually a full 2 gigahertz of at least digitally 2 gigahertz of measurement bandwidth. And resolution on the outside on the output is 14-bit, on the input is 12-bit.
Then let us have our colleagues from the Advanced Quantum Test Bed at Lawrence Berkeley National Lab in the US join us.